Okay, so the first test for chi-square is called the chi-square goodness of fit. So goodness of fit, we use this. So chi-square tests are used only with proportions. When we have um, many proportions, not just one or two, like we've been doing one sample or two sample, but when we have many different proportions, we use chi-square. The first test we're going to use is a goodness of fit. So goodness of fit uh, test is to check to see how good the data fits the claim. So a goodness of fit test is used to determine whether a population has a certain hypothesized distribution expressed as proportions of individuals in the population falling into various outcome categories. So there are two types of goodness of fit tests, and we'll do one of each. The first one we're going to do is actually the second one, fixed or given proportions. So the first problem, the first example we're going to do with the M&Ms is to see if the data, our given data, fits a fixed or given proportions, which is the claim. Okay, so the proportions are expected to follow given values. The other type, which is example number two, is if we're checking to see if the data fits equally. So all proportions are expected to be the same value. Okay, so we'll do one of each. So the hypotheses for goodness of fit tests will always be, the null will always be the stated distribution of the categorical variable in the population of interest is correct. So not word for word, but essentially that idea that whatever was the claim is correct. Whatever the claim was is correct. The null, the alternative will always be it is not correct. The stated distribution in the population of interest is not correct. So for chi-square, we almost always write out our hypotheses in words as opposed to symbols like we've done in the past. Okay. The formula for chi-square for all chi-square tests is this right here. It's written on your formula sheet, so it's not something you need to memorize, but um, it's the observed count. So observed count means the given. What was given? What did we actually see? Minus the expected count. What would we expect to see? Squared. That goes on top. And on bottom is the expected count. This little thing that looks like an E is a summation notation. A summation notation means when you find a grand total, you add them all up. So we're going to get many chi-squares, but we're going to add them all up to get one final chi-square. Okay. The expected counts. So I'll show you how to do expected counts, but you can read this little part here. Conditions, we only have two conditions. So luckily there are only going to be two conditions for chi-square. Okay, I'll show you that when we do the problem. Degrees of freedom, n minus 1. N minus 1, and n being the category. A category, not n being, so n is going to be a category or number of categories. It won't be sample size. It's one of the differences. Okay. The calculator, how to use the calculator, I'll show you in class. When we get back to class, I'll show you how that works. So, okay, so I already kind of did this problem, worked it out, but I'll walk you through it. Okay, so Jerome's class wondered if the distribution of color in a large bag of M&M milk chocolate candies differed from the claimed distribution. So here's what he actually saw. So what Jerome actually saw was he had 12 brown M&Ms, 3 red M&Ms, 7 yellow, 9 green, 9 orange, and 20 blue, 60 total M&Ms in there. Okay, so if we wanted to find out the proportion of blue, we would go 20 over 60. All of these guys are over 60 to see what proportion for each. So we really have 1, 2, 3, 4, 5, 6 sample proportions. We have 6 sample proportions. So it's more than 2 sample. So what we're trying to see is if this data fits what was stated. What is stated? Well, here's the claim. Here's what the Consumer Affairs Department of the Mars Inc., the company who makes M&Ms, says should happen. They say out of all of their M&Ms, 12.5% are brown, 12.5% are red, 12.5% are yellow, 12.5% are green, 25% of them are orange, and 25% of them are blue. That's what they say in all of their M&Ms. So what we're trying to see is if this sample fits the claim. This is the claim. Okay? Okay, so the observed. So the observed is just what we saw. 20 blues, 9 orange, 9 green, 7 yellow, 3 red, 12 brown. That's what was actually in the pack of 60. Okay. Expected. How do you find expected? Well, I took the total number and multiplied it by what I expect. So for blue, I expect 25%. So I took the total number, multiplied it by what I expected, and I get my expected value. So for blue, I would expect 15 of them to be blue. So you can see I got a few more, or I got 5 more than I expected. Could be chance, could be something significant. We're not sure. That's why we're doing this test. Orange had 6 less than it was expected. Green, only about 1.5 off. Yellow is the closest, only half off from what I expected. Red is pretty far off, and so is brown. Okay, that's the expected. So then I use my formula. See, I use my formula 6 different times to come up with all of these numbers. All of these are chi-square statistics. Okay. Now, when I add them all up, I get my overall chi-square statistic, my test statistic. Okay, so it's not a t-score or a z-score, it's a chi-square score. Okay, so my chi-square score was 9.8. So chi-square, we do have chi-square tables. Chi-square tables are the only table we haven't used thus far. It's the very, very last table with the t-score. It's the one that's skewed to the right. So chi-square is always going to be skewed to the right. Okay. So when we're doing this, what we do is you're going to look up, so we're going to use our chi-square overall score with our degrees of freedom. Well, remember, degrees of freedom for chi-square is categories or proportions minus 1. So we have 1, 2, 3, 4, 5, 6 categories, 6 proportions. So this degrees of freedom is going to be 6 minus 1, so 5 total. Okay, so that's why I've highlighted line 5. Degrees of freedom is 5. So what I'm going to do here is I'm going to find this number in that yellow line. Okay, and I actually shaded the wrong side. Chi-square, we always shade to the right. So chi-square, we always shade to the right. Okay. In chi-square, the reason chi-square is skewed to the right is because there are no negative chi-square numbers. You will always get positive chi-square numbers. They might be small, they might be big, but you're always going to get positive chi-square numbers because we square it. So even if you have a negative on the inside, you're going to square to make it positive. So because of that, chi-square is skewed to the right. Most chi-squares are on the lower side, but there are some chi-squares that are on the bigger side. So we're trying to see what percent that is. It's still 100% under the whole thing, just like the normal curve. So it's still 100%, but it's just skewed to the right. Okay, so we also do calculations first. I forgot to mention that when we do chi-square, we always do calculations first. Okay, so if I'm talking too fast or you miss something, just pause the video and then kind of go back and see, okay? So to calculate the percent in the pink there, we're going to go find our chi-square. So 5 degrees of freedom, 9.8. So 5 degrees of freedom, 9.8. So 9.8 is in between these two guys. So we go straight up. Let me highlight that. Okay. The top is the percent. So we are in between 5 and 10%. 5, oops, nope, wrong one. We are between 5 and 2.5%. Sorry, 9.8 is in between. Wait, no, I was right the first time. Sorry, I was looking at the wrong line. We're looking at this number here and this number here. Both of those guys are going to be our chi-squared, or where our chi-square is in between. So we go up. This is the percent. So the percent in here is between 5 and 10%. Okay, it's between 5 and 10%. Bigger than 5, less than 10. Okay. So that's as far as we need to go in our calculations. Our population parameter is, we have 1, 2, 3, 4, 5, 6 different categories. So I try to put them all together because they each represent a color, right? Blue, orange, green, yellow, red, brown. And the P is proportion. So the true proportion of different colors in the bags of M&Ms. That's what all those P's represent, right? All of these P's, right? 20 out of 60. These are all P hats. But we're trying to figure out the true proportion of browns, true proportion of all of the reds, not just the one bag. Okay. Our hypothesis is the distribution of colors is correct, as stated. The claim. This is the claim. They've told us that 12.5% of the brown are going to be brown, 12.5 red, 12.5 yellow, 12.5 green, 25 orange, and 25 blue. Okay. The alternative hypothesis is no, that's not correct. Which one? It doesn't matter. It doesn't say I think brown is incorrect or blue is incorrect or red is incorrect. It says just one of those, because if one of those is incorrect, that means the others have to be incorrect, right? If the true proportion of blue is not 25%, then that would affect orange, green, yellow, red, brown, right? Because all of them have to equal 100%. Okay, significance level, we didn't say, so 5%. SRS, it was a random sample of 60, right? Random sample of 60, so we're good there. So here is the second. There's only two conditions here. First one is SRS. Second one, all expected counts have to be greater than 5. So all expected counts. So all of these numbers here, we had 6 expected counts. They all have to be greater than 5 for that condition to be met. So they all are bigger than 5. So we would say, yes, 6 out of 6 are bigger. So that's 100%. Okay. Our test statistic that we used, chi-square and degrees of freedom, we've used, and we already did calculations, so we're good there. So the last thing is conclusion. Okay, so conclusion. So conclusion, it's the same 3 things. The first thing is p-value. Since p-value, let's go back up here, p-value for this one was right here. That was the p-value between 5 and 10%. Okay, bigger than 5, less than 10. Since p-value, we can just say 5 to 10%. is greater than alpha level, which is 5%. Since p-value is greater than alpha, we always fail to reject the null hypothesis. Okay. That takes care of 1 and 2. Therefore, we lack sufficient evidence to show, and then we're going to try to put the alternative in context. Okay, so let's scroll back up for the alternative. The alternative was they're not. The claim is wrong. So we don't have enough evidence to say the claim is wrong. So we don't have enough evidence to say that these percents are wrong. Okay, so we're going to say we lack sufficient evidence to show that the given distribution of proportions is incorrect. We lack that evidence. So we don't have enough evidence to say that any of those are wrong. So are they right? We don't accept. We never accept, right? So we never accept any of these. We just say we don't have enough evidence to say any of these are wrong. Okay. One other thing, the last thing, the one more thing they might ask you is which category had the most influence on chi-square. So all of these numbers were added up, right, to make chi-square. So to have the biggest influence means the biggest chi-square. So in that case, it would be red and brown. Those two had the biggest influence on 9.8, right? The reason it had the biggest influence is because if you look at their observed versus the expected, there's the biggest difference between those two guys, right? The smallest chi-square statistic was yellow because that one was the closest. The observed was the closest to expected. So that's another question they might ask. Okay.
So we have counts of 256 randomly selected executives in 12 astrological zodiac sign categories. So have you guys heard of the zodiac signs? Okay, you guys have had some familiar with it. It deals with astrology. Okay. Yeah. Mm-hmm. So the natural null hypothesis is that birth dates of executives are divided equally, so it doesn't matter. So they're trying to say, does it matter? Are all executives equally distributed between the 12 signs, 12 astrological signs? So pretty much you just, when are they born? Are they born? They want to know, are executives born during a certain time more likely than others, or are they born just kind of, does it not matter, right? That's what we're going to test. The test statistic looks at how closely the observed data match this. So it should be match. That should be match this idealized situation. Are zodiac signs of CEOs distributed uniformly? What does uniformly mean? All the same, right? People who wear uniforms, they all dress the same. Uniformly, right? So uniform, they're going to use that word a lot. So when they use that word, that means chi-square, goodness of fit, equal proportions. Sometimes they might just say, are they the same, or distributed similarly, distributed the same? You know, obviously we know what it's going to be because it's in the notes, but I'm talking about when you see it on an FRQ, are you going to know this is a goodness of fit test? Okay, because that's the key there. Looking at some of your tests on the multiple choice, I think some of you were confused as to which kind of test to use because there were some that were off. Okay, so I just want to make sure, what are we looking for here? So this is a big word here. Do this data. This is the observed. So there were 23 executives who are Aries. Aries means they were born from March 21st to April 19th. So right now, they were born from March 21st to April 19th. 23 were. Taurus, if you were born from April 20th to May 20th, you are considered a Taurus, so on and so forth, right? Okay. All right. So 23 of them are considered Aries, 20 of them are considered Taurus, 18 Gemini, 23 Cancer, and so on and so forth, right? Okay. So if we were doing, so let's do calculations like we did first. Let's do calculations first, since we have the table already set. Sometimes they won't give you a table. This time they did give you a table. Okay, so let's do our calculations right now. We know it's chi-square. We know it's goodness of fit. So expected counts. What are the expected counts going to be? How do we find expected counts? There you go. If they're evenly distributed, uniformly distributed, the same distribution, that means everyone should be the same, right? So each one of these 12, we should expect how many? 21.33. So let's go 21.33 for all of them. Okay. We didn't have to calculate anything, or you just calculated divided, right? You just divided. So this one's different. This one is different than how we calculated this table here. This table here was calculated a different method for expected counts, right? So it just depends on which one it is. They're both goodness of fit tests, but they have different way of calculating expected values. So just be careful there. Okay. All right. So calculations. So now we're going to do chi-square. This one has more. So I'm going to show you the calculator. We'll do this one using the calculator. Okay. More so than we did the first one. Okay. So, chi-square says, so to calculate chi-square, what we're going to do is we're going to find the summation of observed minus expected squared over expected, right? We're going to do that for each one of the 12. Each one of the 12. So the first one would be 23 minus 21.33 squared divided by 21.33. Okay, so this is what we're going to do. This is the work we're going to show. And then we'll go to the calculator. So I'm going to show the first two, how the first two are calculated. So the one I just did. The one I just did. 23 minus 21.33 squared divided by 21.33. Plus the next one. The next one would be Taurus. For Taurus, it's 20 minus 21.33 squared over 21.33. Plus dot, dot, dot. Continues on with that one, and then I would do the last one, which was Pisces. Pisces is 29 minus 21.33 squared over 21.33. Okay, that's all the work we need to show. The rest of it, we're going to use the calculator. I'll show you how to use the calculator on this one. Okay, so we're going to calculate our chi-square statistic for all of them and add them up. Okay, so let's go to the calculator. Okay, so when we go to the calculator, first thing we're going to have to do is we're going to have to make lists. One is observed, one is expected. So let's go make a list. So 23, 2018. 23, 2019. Okay. So there's a fast way of doing that. You can do it. You can do it the same way, but there's also a faster way of doing it. Say enter all of these values here. I want you to go 256 divided by 12. Oops, why won't let me do that? Let's see. What did I do wrong? $256. Oh, maybe I need to put divided by in here. Divided by. Nope, I guess not. There was a way to do it, but I guess for some reason I'm not doing the right thing. So 21.33. There's a way to cut and paste in too, but I just don't know how. There's ways to do it. I don't really use that a lot, so I just don't know how to do that. I haven't looked it up. Okay. So we're going to create a new list. We're going to create a third list. When you want to create a new list, you got to go to the top, highlight the list, hit enter, and then you should have a blinking cursor at the bottom. So how do we calculate chi-square? Okay. So how do I use it? I'm using my list. Okay, so I'm going to do that. Parentheses. L1, that's observed, minus expected, L2, squared, divided by L2. Hit enter, and there's your chi-squareds. Okay, so it'll calculate them all in one big shot. Now, how do I get my total chi-square? Because each one of those represents chi-squared for each one, right? So how do I get my total chi-square? One var stats. So we go one var stats for L3. Nope, not L2. L3. Oops, no. Yeah. Let's see here. Clear. L3. So the one with the sigma, there's two of them with sigma. One with sigma squared, x squared, and one with regular sigma. I already squared them. That's what the formula did. So the one I'm looking for is the one without the square. Nine, 4, 6. Okay. All right.
So we're going for the one without the square.
Okay. I already squared them, so I don't want to square them again. Okay. Now, that's just a faster way of doing it. You don't need to do it that way, but it's just a faster way of calculating chi-square for each of them, especially when there's a long list of them, and then adding them all together real fast. But you do not need to do that. I find a lot of people say, I don't have a calculator. Like, no, you don't need to do that. You just do each one of them individually. It'll take you another 5 minutes. But what's 5 minutes to get an A, right? Okay. You can calculate, you literally can use a dollar store calculator to do that problem right there. And then you just do that for all the rest of the 12, add them together, and you'll eventually get that. Okay. But it's just, since we have these calculators, we use them. Okay. All right, degrees of freedom. Degrees of freedom. What are we going to have for degrees of freedom here? 12 categories minus 1. If it's calculations, we have to show how we got the calculations. Okay. P-value. P-value. Since this is calculations, we also need p-value. So we go to 11. It's going to be on the left, on the extreme left. Right? It's lower than the extreme left, the last one that's extreme. So it's going to be even lower than this. A lower chi-square means a higher probability, though. So it's going to be greater than 25%. All right, so let's put greater than 25. Okay, there's the p-value. Okay. All right, so that's all calculations. So let's go on and let's fill in the rest of the holes that we skipped on their way here. So population parameter. You got a lot of proportions. Just like the last one, we had 6 proportions. How many proportions are we going to have? We had 6 proportions, one for each color. How many proportions are we going to have here? 12, one for each sign. Okay. So we don't have to list them all. We just have to be general with how we label them. Okay. So let's see here. So yeah, so we don't have to list them all. You could just go the first two, AT, ... The last one is Pisces. True proportion of what? True proportion of, that's for one. Like if I was doing just for Aries, that would work. But I'm not doing it just for Aries. I'm doing everyone together. So what do I have to put? What word do I have to put in there to show that I'm doing everyone together in one swoop? No. If only we did a problem like this before. No.
Every month?
No.
All months? Yearly?
No.
Oh, man.
See, the way you guys are thinking, we would have just for one.
Right.
Right? I don't want to do one. I want to do them all together. I want to look at all of these numbers together. No, missing something. What are you looking at here?
All of the months.
I think someone said it.
Was it hard for us? Is it
I think I heard the word.
each? He said each.
Nope.
All?
I think I heard the word somewhere, but no. Do I really have to scroll back? You guys have it. Well, you should have it. Oh, we don't have it. Don't have it there. I should have had it there. Okay. True proportion of distributions for. I'm not looking at just one number. I'm looking at many numbers for many things. So if it's many numbers for many things, we always want to use the word distributions. Okay. Otherwise, we just think it's one number. Okay. That's the word we want to use. Distributions. Distributions of what? It's right here. Distributions of. It's not about the month. What's the question asking? Their sign, right? Distribution of zodiac signs for CEOs. Right. In practical terms, it is the month. It is the time of the year that counts, right? But that's not the question. The question is referring to the zodiac sign. So we want to make sure we include that. Okay. Next is hypotheses. We have the null and the alternative. Okay.
Doesn't the prompt say the null hypothesis?
What?
Isn't the natural null hypothesis is?
No.
That's not it?
No.
What is it? City distribution.
What's wrong with the one I have right here? It has no context. Yeah. Automatic strike right there. So make sure you put it in context. So how can I put it in context?
The stated distribution of zodiac signs for CEO is
There you go. Okay. The stated distribution of zodiac signs for CEOs is uniform. Okay. What's the alternative?
It's not uniform.
There you go.
Same thing.
The stated distribution of zodiac signs for CEOs is not uniform. You can rewrite it. Okay, you can rewrite it if you want, or you can use the quotations if you want. Okay. All right, significance level alpha equals in say, so we'll just use 5%. Okay. And then we're missing, we already did calculations already. Conditions, so let's do conditions. Okay. SRS. Stated. How what was stated?
We have counts of 256 randomly selected executives.
So again, what was stated? I'm not asking you to read it. I'm telling you to tell me what. No. What's stated?
How they were randomly selected.
Not. Did they tell you how they randomly picked them? No, they didn't. Why? What is stated though? There you go. That there was a randomization to select CEOs. Okay. Number 2. All expected counts are greater than or equal to 5. So we go back to our table. Yep, they're all the same. Since this is uniform, they're all the same and they're all above 5. So 12 out of 12. Yes. 12 out of 12 equals 100%. Okay, and then the last condition, 80% of expected counts are greater than 1. Uh-huh.
So why does the third condition exist if the second one already?
Exactly. I was waiting for someone to say that. Actually, I said that yesterday, but no one brought it up, so I kept doing the third condition.
It's actually the same thing.
Exactly. So if you know that, we don't even have to do this guy, right?
Why are they still gonna check for it?
No, because you already did it. It's redundancy. But I kept doing it because no one brought it up. I had mentioned it yesterday, but no one brought it up, so I kept doing it. But yep, if you notice that, it's redundant. Because if all of them are 5 or greater, then of course 80% of them are going to be above 5 or above 1.
Nice. If you don't meet the second one, do you have to do the third one?
Yes.
Yeah, that's true. If you get the second one, the third one, right?
Well, there you go.
Not necessarily the third
If you don't remember that, just do all 3 of them. It doesn't hurt you to do all 3 of them. Won't take any points off to do all 3 of them. So the way I did it for the first one, nothing bad will happen. Okay. Test statistic. Okay. So we already did all of this, but which test statistic do we use? Well, it's chi-square. So any chi-square test is going to use chi-square test statistic, which is given. Other side. Very bottom. Okay. And then degrees of freedom we also used. Categories -1. And then the last one is conclusion. Okay, since on that one, p-value, which was greater than 0.25, is greater than alpha, which is 0.05, we fail to reject the null hypothesis. Okay. Therefore, we have sufficient or significant evidence. Yes, you're right. We do not have, or we lack to suggest or to show what?
But the distribution of zodiac signs for CL is uniform?
There you go.
Or not uniform?
Is not uniform. Good. To show that the distribution of zodiac signs for CEOs is not uniform. Okay.
What would we put for the first sentence if it is between two numbers?
Okay, good question. So let's say I have two answers to that. I'll show you the first answer. Let's say it's between, let's say we had a right here, right? Let's say we had one right here, which is between this guy and this guy, right? 0.05 and 0.025. So let's go back.
So you could fail. There's a chance to fail to reject.
Okay, so where is it? So first of all, we'd say 0.05 we can say p value. So in between there, right? We'd say that instead. Would we reject or fail to reject this guy? Can't do both. So let's say I had this one instead of
Oh, you failed to reject.
this guy. Oops, no. Instead of this guy here. Would we reject or would we fail to reject? We would reject. Why reject?
Oh, right.
It's going to be smaller than 0.05 because there is no equal sign here. There's no equal sign, right? For it to be exactly 0.05, it has to be exactly this guy here. We didn't say it. We said it was between these two guys, right? So if it's not this guy exactly, if it's in between them, that means it's in between. It's not. Okay? Yep. The second way, I'm going to show you the second way. The second way is using your calculator. So go to your calculator. You got everything in L1 and L2. So you're good there. Go to tests. The list of tests and intervals that we usually have. There you go. So you're going to go all the way to the bottom. There's two, right? There's two chi-square tests. Yeah. There's one that says chi-square tests, and there's one that says chi-square GOF or GOF test. What do you think GOF stands for? Goodness of fit. So we're going to use that one. Observed, where's our observed? Where's our expected? How many degrees of freedom do we have? I'm going to do draw just to show you, because remember chi-square is skewed. With chi-square, you always shade to the right. You always shade to the right. So here is our chi-square, 5.0946 right here, and then they always shade to the right if you're doing chi-square. Okay? That's a big portion, right? That's a big portion. So that's why our p-value was a lot bigger than 25%.
Will the p-value and the alpha level be equal to each other?
No. If the p-value and the alpha level are exactly equal, I've never seen that ever.
Okay, so I did something wrong.
Because that's how we determine if we reject or fail to reject. So they'll be close sometimes, but they'll never be exactly. Okay. All right, so that's goodness of it. So the assignment, it's from your book. It's from 11.1. Okay, so tomorrow we're going to start on 11.2. 11.2 is 2 tests. There are 2 chi-square tests. One of them is homogeneity of populations, and the other one is test for independence or association. Okay, they're very similar. They're very similar, and they're done exactly the same way, but they're just for 2 different things. Okay, we'll talk about it tomorrow. Okay.
Okay, so why don't we do